All right, welcome to part 4 of our lecture video series from Monday, March 13th. So we're going to get into the information that can be gleaned from a molecular orbital diagram. In other words, why do we care? Like, why is MO theory something that's important to us? Isn't Lewis kind of good enough? At minimum, isn't valence bond theory good enough? Like, why MO theory? And this is because MO theory allows us to make some really interesting observations and predictions about the inherent strength of bonds that are formed. In other words, it allows us to predict the stability of a molecule that's formed based on the arrangement of electrons or placement of electrons in different molecular orbitals. So why is that? Well, the answer is actually rather simple. A molecule is more stable if it has a large amount of electrons in bonding type molecular orbitals. In other words, if we have a large bond order, so let's define bond order. So define bond order. So bond order is the strength of a chemical bond as predicted by molecular orbital theory. And we would find these bond orders to be analogous to things that we've seen in Lewis and VBT, which is the idea of single bonds, double bonds, or triple bonds. So how do we calculate bond order? So bond order, BO, is equal to 1/2 times the difference between the number of electrons in bonding type molecular orbitals minus the number of electrons in antibonding type molecular orbitals. So bond order, strength of a bond. And this gives us information about overall molecular stability, because if bond order is high, then we formed a really stable molecule, right? We know that it is harder to break something like a triple bond. So since it's harder to break, then that triple bond is going to be lasting out for a long time, meaning that molecule is going to hang out for a long time. So I've drawn here on the left at least kind of parts of our molecular orbital diagram from fluorine that we did in our prior video. And I want us to see if we can't calculate the bond order of fluorine and predict whether or not this is a stable molecule. So in order to do that, I need to figure out the number of electrons that are in my bonding molecular orbitals. And then I also need to figure out the number of electrons in my anti-bonding molecular orbitals. So if we looked at our electron placement, that was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay, so let's go hunting for our number of electrons in bonding molecular orbitals. So I've got my sigma s, that's a bonding, my other sigma s, that's a bonding, my sigma p, and then my 2 pi's. So for fluorine, I would calculate the bond order as being 1/2 times the difference of those 2, 4, 6, 8, 10 electrons in my bonding orbitals And now let's count up the number of electrons we have in our antibonding orbitals. So let's see here, we've got our sigma s star, that's 2. Our other sigma s star, that's 2. And then we have 4 total in our pi star antibonding orbitals. So that is 2, 4, 6, 8. So that is 1/2 times 2, which is equal to 1. So the bond order is equal to 1 in F2. And you and I would think of this as being like a single bond. In fact, if we look at Lewis, let's see if a single bond is predicted. So I've got fluorine, fluorine, each with a total of 7 valence electrons. Connect them. I've used up 2. Fill in their octets. So let's see, I've done 14, used up 2. That's 12. 2, 4, 6. That means I have 6 remaining, which is just enough to fill in the octet of my other fluorine. This predicts a single bond, meaning that we have good agreement between what our Lewis predicts and what the molecular orbital theory predicts. You would also expect to see a sigma bond being formed based on the hybridization of each fluorine, which would be sp3. We have one orbital containing our spin pair electrons and the remaining containing lone pairs on each of the fluorines. So if you want, I can draw that. So we'll have our tetrahedral arrangement of our hybrid orbitals. From each of our fluorines, where in this overlap region, this is where we create our bond, and everything else contains our lone pairs. Okay, so from an MO diagram, we can get the bond order, which tells us the relative strength or stability, strength of a bond or stability of a molecule. All right, what else can a MO diagram describe or give to us? Like, why do we care about them beyond looking at bond order? As mentioned earlier, we can deduce some physical properties from MO theory that are not necessarily obvious from things like valence bond or even Lewis theory. Specifically, one of those physical properties is this idea of paramagnetism or diamagnetism. So that is going to be our final topic for today, Monday the 13th. I think we're going to save SP mixing for Wednesday the 15th, because it's kind of our special cases where our MO diagrams are not energetically structured as we might predict. So we'll end today off with para and diamagnetism, and then that will be it.